Keep Olivia. I know, especially because we're going to do chemistry. Too bad. Deal with it. Let's see. This. Oops. Like a damn singing bell, I get for you. You look happy and healthy, not me. Where were we? We were here. Okay, so welcome back. Oh, the crowd is just dwindling. 8 o'clock in the morning. We don't even, tomorrow's Wednesday, we don't even have a pop quiz scheduled. We can't even do, we could schedule it. Be short notice. We are talking about the interaction energy now. So we've got to the point where we have particles, and initially we said they don't interact with each other. So if they're in the gas phase and they don't interact with each other, we had these nice, beautiful properties. The pressure was proportional to the temperature. The pressure was proportional to the number of particles in the system. And that was all very handy. That was ideal gas behavior. We're talking about real gases now, and the difference, there's two. The one, they take up some volume. It's not very much, but they take up some volume, but they have attractive forces between them. So each particle creates a potential well for any other particle that comes close to it. So in a sense, those collisions aren't going to be perfectly elastic anymore. In general, energy is very well conserved. If energy wasn't well conserved, then the gas would always just continue to cool off. So, but you can have a kinetic energy situation where you get trapped next to each other, and trapped next to each other is condensation. That's changing the phase. So we're not going to talk in detail about the forces, intermolecular forces themselves, and it's hard to sort those out of the homework. So we're going to get to them again, but in some of the homework you might be asked to name the intermolecular force or something like that. We're not going to do that. That won't be on this midterm on Tuesday. So if you see those kind of questions where you're really in the nitty-gritty about intermolecular forces, you know, where do they come from, what are they called, that kind of stuff, that's all depends on the electronic structure, and we'll talk about that later, and we'll bring it back when we talk about that. For now, we just have to say, yeah, sometimes they attract each other, and that's all we need to know. So if they attract each other, then for an ideal gas, we said there's never any attraction. So if you plotted the attraction versus how close they were to each other, the attraction energy, and we did this, we've done it already. We've said a negative charge coming close to a positive charge. The attraction energy depends on how close they are, depends on the distance r between them. But if you have no attraction energy, you're in the ideal gas state. And you're in the ideal gas state, the energy is directly proportional to the temperature. The slope of that line is related to R, the gas constant, as you know. So here we could write it down. For the average kinetic energy for a particle is 3/2 kBt. And if you multiply kb by Avogadro's number, you get R. So you could do that for a mole as well. But what about the case where there is an attractive force? So that's the case that we can show here. And if we could get a shot, I don't think we have to do camera 4 first. If you just do a little bit tighter shot here on me and put it up there, right down where you can kind of see the bench top here. Yeah, that's good. So this is the case where these balls, if they're flying around in a gas phase, ooh, you see how they touched and they affected each other? If there's a little bit of attraction between them, they could get trapped in their mutual potential well and stick together. They could condense. And real particles do this. And I think we're going to go to camera 4 for this one and get this. We did this once already, but it's so cool. I like to do it, and we're going to do it one more time when we find out what that is about water that makes this happen. But we saw that water has this ability, or something in the water is forming an attractive interaction with a negatively charged rod. So the attractions to this negatively charged rod happen between the molecules themselves. And that's why water does condense, why it has such a high boiling point. Because there are strong attractive forces. We saw that very large van der Waals parameter A for water because a lot of attractive forces. So if I allow water to stream down here and I bring the rod next to it, look, I can make that whole stream of water bend towards the rod. Let me see if I can charge the rod up a little more. So I'm just rubbing off some electrons. Look at that. Oh my gosh. I can bend the water right towards a negatively charged rod. Hexane, different liquid, and different liquids will have different attractive properties. That's unaffected by bringing a charged rod next to it. So it doesn't have this property. And it has a lower boiling point, lower intermolecular interactions, intermolecular forces for hexane. So we say that there's some interaction energy. As the particles for the real gas, as the particles come close to each other, there's an attraction. And I have to say, well, do I have enough kinetic energy to avoid being trapped there? Do I have a kinetic energy that's greater than that attractive energy? And you know, at high temperature, high kinetic energy, you will have enough to stay away from that potential well. But you could get trapped in that potential well if you have low kinetic energy. And there you can kind of plot it. You can say, well, here's for real gases. And if you're at high temperature, even real gases behave ideally because in general, the average kinetic energy is much greater than this attractive energy. But when that attraction energy is about Boltzmann constant times the critical temperature, where these real behaviors start to come into effect, then you start to see condensation at about that energy regime. So, which particles have it? Oh my God, this is fantastic. Everything we've learned virtually in chemistry just spread out across the board. You can say, well, I can go to the energy consistent with the critical temperature, can I? Because this is a kinetic energy, and that kinetic energy is associated with a temperature. So here's plotted at the critical temperature that Boltzmann distribution. And these particles, so here is that particular velocity associated with the VRMS, root mean squared velocity, that is associated with a specific energy at a specific temperature. And if you go to temperatures below the critical temperature, look how many particles, oops. I thought there was another animation where I shade these. But more particles start to have less on average than this attraction energy. So as you go down in temperature, those kinetic energies become less than this potential energy, and you're going to condense. So all of our we've applied all of our horsepower, everything we've learned so far in the class, to understand condensation. And we do have a little demo where you can look at that. So here's the case. I can take this particle and I can pull it to very far away. So very far away, the particles don't interact. We know the zero in energy is when they're very far separated. As you bring them closer, the energy goes down. Why does the energy go down? They're coming together. So we know I always have to think about the other way. If they were going apart, I would have to put energy in. So that must mean their energy would go up. I would be putting it in. If they come together, their energy must be going down. And indeed, that's what's happening. Their energy is going down as they come together. And if they have low kinetic energy, they can get trapped in this well. But it is kind of a trapping. So if I think I can just give it some kinetic energy, and you can see that kinetic energy is not enough to escape that well. It's like Chloe Kim trapped in the half pipe. But I can probably give it more kinetic energy. No, try again. That wasn't enough. Let's try again. Let's see if I can arrange it so I can push it harder. I'm not sure I can actually change the kinetic energy. Let me try it like this. Ah, there. You see, I gave it too much kinetic energy and it bounced right out of the well. Its kinetic energy was much greater than the return atom. Return atom, please. Return atom button comes up. So lots of kinetic, oh shoot. I have to have the animation going. And lots of kinetic energy. That's not enough. It gets trapped. Let's try to give it some more. Do I have to reset? Let me reset, because maybe it gets stuck with that kinetic energy. No, doesn't seem like you can just push them. Oh well. Anyway, you get the idea. So there it is, potential wells, and you can see if you we put the attractive forces on there and we really increase the attraction force, and let's get a smaller diameter the atom so we can see it. As they come together, watch this attractive force start to grow. See that attractive force start to grow as I get down there, and very big attractive force. But watch what happens if they get too close. Then this says, oh, you're too close, and the energy starts to go up. You're crushing us together. You're putting us too close together. And this is where I'm comfortable, right down here where those things are balanced out. So that's a nice demo. That one's in your notes. You can play with that if you'd like. So this is just summarizing that, like we did with the balls. High kinetic energy, you can have the balls blow by each other. Here's the ideal case, no attractive forces. In the real case, there's attractive forces. But the temperature is high enough that T times KB is much greater than that potential energy. So the potential energy, what you're saying here is the kinetic energy is bigger than the potential energy. Low temperature, lower kinetic energy. Now the kinetic energy and the potential energy are about the same, and you have the potential to get trapped in that potential well. Okay, so we have continuous density increase. Here we have a phase change because you form the liquid or solid phase. Okay, we're gonna just talk through this one together because I showed you the data yesterday, so you might not remember it or have it. Which has the largest, the most negative U, so biggest in magnitude here. It's a negative energy. Remember, we set the zero of energy up here. All attractions are negative attractions. As that comes, energy is released downhill, negative, released downhill and negative. All those three things should go together in your mind. So which one? And we already know water has the greatest interaction. We said it last time. Helium, almost no interactions. Carbon dioxide, some. Water, more. And you would be able to characterize it if you look back at that table. And in general, as you know, I don't want you to do calculations on the exam, so I'm going to ask you questions more like this, where you just look at the relative magnitude of these things, and you predict a boiling point, or you predict a kinetic energy where they would be likely to condense. And you can see boiling point goes up, or condensation point, that's the same point, where the attractive force is you get to a temperature, you could say either high enough, if you're going up in temperature, high enough to overcome the attraction energy, or as you're going down in temperature, it gets low enough that the attraction energy wins and you condense. Okay, we will go on the next thing, which I think is here, probably. So we're going to continue our discussion. Here's our roadmap, as we always start out with. We're going to continue to talk about bulk matter, gases, liquids, and solids. And now we're going to talk. There's Skittles in my pocket. These pants have not, okay, that's kind of, all right, I won't tell you that, but these pants haven't gone through the washer since Skittles Day. I haven't been wearing them the whole time. So now we're going to talk about phases of matter in more detail, and we've been doing this, we've been showing you these phase diagrams and just kind of hand wavy. We're just going to look at them in more detail now. So a phase diagram, now this is pressure temperature space that we look at these in. Sometimes we look at pressure volume space when we're looking at ideal gases, but we can look at any coordinate system we want, pressure temperature space here. You could think of it in 3 dimensions. You could think of it as volume coming out here on this axis if you want. It'll probably hurt your brain. If you go on in physical chemistry, that's what you have to do. You have to think about the 3-dimensional surface. And then you look at how the temperature changes with energy, and the slope of that is the heat capacity. You'll rack your brain like crazy. But we're going to try and stick in one plane. And if you look at high temperatures, low pressures, you should see a liquid. Lower pressures and higher temperatures, you should see a gas. And low temperatures and high pressures, you'd expect to see a solid. So basically that's the landscape, but there are clear dividing lines between them. At all these points, it's equilibrium between the solid and the gas, the gas and the liquid and the solid. So here's where we melt, constant pressure, increased temperature, we would go from solid to liquid. There are a couple points to be aware of where they all come together. We talked about this when we talked about balancing the free energy of the universe, balancing the entropy of the universe. At this point, the universe is indifferent to whether you are a solid, liquid, or a gas. You can equally exchange. All three of them are in equilibrium. When a particle goes from solid to gas, the entropy of the universe doesn't change. And we know why that is. That's a big entropy change for the system, but it takes a lot of enthalpy, so that makes the entropy of the universe go up, or excuse me, down. So big entropy change plus by going from solid to liquid or solid to gas, but it takes energy to do that. So we gain that entropy in the system, we lose it in the surroundings, and those things balance out at equilibrium. That is what equilibrium is. And you can have equilibrium between all three phases. At the triple point for carbon dioxide, that happens to be 5 atmospheres and minus 56 Celsius. That's the coordinates of that point. There's also the critical point. We talked about that last time. The critical point, notice that the liquid gas equilibrium line terminates at a point. And we know why that is. This is the critical temperature. Above the critical temperature, you don't see that phase boundary anymore. You don't see, it stays one phase as it condenses down. And we'll look at that in a minute. That's 73 atmospheres and 1,000 psi. So this isn't quite to scale. You can say 1,000, oh, well, that's psi. This is atmospheres. I don't even know what the conversion between psi and atmosphere is. Oh, wait a minute, it's right there. It's about 0.07. 73 atmospheres is 1,000 psi. So very high pressure and moderate temperature. That's about hot room temperature. Here it is for water. And in general, all the same kinds of things. You'll have a triple point. At this, for a triple point for water, is about 0 degrees Celsius, but very low pressure. So 0 degrees Celsius and 1 atmosphere of pressure, you'd be in the solid, but 0 degrees Celsius and very low pressure, you can have all three phases. And of course, it has a critical point, critical temperature as well. Critical temperature for water, extremely high, as we would expect, because water, very strong intermolecular forces. You have to go to very high temperature for it to behave ideally. And 215 atmospheres there. So let's look at this. First, let's cross this line. Let's go somewhere where we have gaseous. Go to a point where we have carbon dioxide gas and increase the pressure until it turns into a liquid. Go across that phase diagram there. And in general, these points, this whole line is kind of out of the range. We don't see liquid carbon dioxide. We see the gaseous carbon dioxide. So these are not in the range of normal pressures and temperatures that we have in the room. But you can do it. And I asked Karen, and she said that demo broke. Well, we should just be able to push this button. Here's Lonnie. He'll do it for you. So he's got gaseous carbon dioxide in this cylinder, and he's going to squish it with this column of mercury, and you can see as he squishes it, there is liquid carbon dioxide being formed, and you can see it evaporating or condensing, however you want to look at it. We've made liquid, and then as we reduce the pressure, we see the liquid gas equilibrium of carbon dioxide. That's really cool. Of pressure and temperature. We can also see this triple point. This is really cool. Let's look at, that's probably here. Maybe not. Push this button. Okay, this person here will explain we'll try to get the critical point of carbon dioxide. So we'll take that liquid carbon dioxide and increase the pressure, but we'll do it above so we'll get to we'll go above the critical point and we'll start increasing the pressure. And the temperature will increase too because of the way they do this experiment. But what you see here is the liquid gas interface between carbon dioxide. So we're at that high pressure place where the liquid and the gas are okay. And you'll see the temperature go up and the pressure go up as this goes. And if we can have the audio out of this signal in the room, you can try to do that, because this guy, I'll let this guy explain it because his accent is hilarious. You guys probably can't hear that, so I'll tell you what's going on. We're just increasing pressure and temperature. And you can see there's an interface between liquid and gas. But now look at this. I'm going to go above the critical temperature. The phase boundary goes away. So we have this dense thing, dense as the liquid, but it's occupying the whole container like a gas. So that's what happens above the critical temperature in this. Oh, what's he going to do? He's not going to open that thing, is he? Oh, now he's going to cool it off. Cool it back off, and you'll go below the critical temperature. And you should see, well, below the critical temperature, both phases will exist. And there we go. Now we have gas and liquid coming back. So two phases potentially at lower temperatures, above the critical temperature, one phase. Thank you, Simon Fuderlieb. Somebody does the triple point of water next. Oops. I don't want them to continue playing. I don't care if they do. Okay, so phase diagrams can be a little complicated. And let me go back. There's one thing crazy about water. Water is one of the most unique substances in the world. And the weird thing is it's one of the most unique substances, but it's so common that we don't realize how unique it is. But for water, the solid-liquid boundary in many places in the phase diagram slopes backwards a little bit. Most slope forwards. What does that sloping backwards mean? It means if you're at solid and you increase the pressure, you should be able to go to the liquid phase. And that doesn't make sense, right? You should say that if you press something harder and harder and harder, you'd think it would tend towards the solid phase, the more compact phase. Well, for water, in certain conditions, most conditions, that atmospheric conditions, the liquid is the denser phase. So you force it back into the liquid phase. And you know that the solid is less dense than the liquid, don't you? Ice floats, solid ice floats on liquid water. And we see that every day, and we think that's the way of the world. Every other solid sinks in its liquid. Water floats, solid water floats in its liquid. It's very fortuitous for us, right? We're here because of that, probably. You can imagine evolution trying to get going. So you got these little molecules starting to coalesce into cells and starting to grow into self-replicating bodies. If water was more dense, the solid, then lakes would freeze from the bottom up. And every year you just have to start evolution all over again because you freeze it all out. So, sorry, this video is playing in the background. I have to go and stop these. Oh, look at that. You could have this guy. Oh, maybe that's me in like 150 years. That could be your chemistry professor. You're probably right now thinking, oh my God, I didn't really appreciate you, Mark, until right now. Just have to stop that. Okay, where were we? We were here. Okay. So that's a very interesting feature of liquid water. And people kind of used to think that's why you could ice skate. So when you ice skate, you put all your body weight, all your mass on a tiny little edge. And that means under that tiny little edge, there's lots of pressure. And that could liquefy the ice and make you scoot across the ice. Modern and actually quite recent research shows that under most conditions, that's not what's happening. You are going to a slightly different phase of the water, but not the liquid. In fact, we have a US team skater in your class. One of your colleagues is Olympic, or fingers crossed, Olympic, Team USA skater. She can skate simply because ice is slippery. It's not any complicated physics. She will tell you it's slippery. You can fall down even if you do it for a living. And here is that complicated phase diagram for water. There's all kinds of solid phases. All these are phase boundaries. All these things. Here's the ones that we were looking at. Just the liquid gas, and here was the solid, and here's that region. And it's right around normal pressures and temperatures where you go increasing pressure, you go from the liquid, or from the solid to the liquid by increasing the pressure. But you have all these crazy solid phases of water. It's a very interesting compound. In fact, you know this if you're a skier or an Eskimo, indigenous native person of the Arctic region. There's in the native languages in the northern regions, there's hundreds of words for snow because it's around all the time and it has different properties depending on the temperature. And you know this if you're a skier too. Some snow is slippery, some snow is squeaky, some snow grabs the bottom of your skis. That has to do with the temperature of the system. So super complicated. Here is ice 3, one of the phases. That phase, ice 3, common around normal conditions. Ice 3 is that phase. And you can see its structure looks hexagonal. These are the oxygens are red and the hydrogens are white. So H2O in an array like that. Geez, can't touch the board. That array, hexagonal array, is reflected as ice crystallizes in the hexagonal symmetry of snowflakes. So let's see if we can do it. Which plot? Now, oh my God, here I'm doing it. Oh, I'm gonna bust your brain. Here, I've got the pressure temperature plot. What does this line look like in pressure volume space? Oh, that hurts your head, but it doesn't hurt your head that much. Let's go ahead and think about that for a minute. So we'll teaching assistants, if you could get up. There are hints for you. Not there. There are no hints for this one, it looks like. Sorry. Talk about it among yourselves. See what kind of conclusion you can come to on this. Oceans Riverside. Okay, let's see what you're thinking about that. Turn on the machine so you can vote. Go ahead, vote on that one. And tell me what you think. Oh, I don't know, Mark Kubinec 859 or something. What did you guys think? Oops. Okay, so B already very popular, and I agree with the B's, of course. If you voted A, I agree with you too. Condensation just means you go from the gas phase. The only non-condensed phase is the gas. All the other phases are condensed phases. So going to the solid is also a condensation. Going the other way, we kind of call it sublimation, going from the solid to the gas. But if you condense, you condense. So here is just decreasing the temperature and going from gas to solid. Here, you're just increasing the pressure and going from the gas to the liquid. Both of those are condensations. What's the vapor pressure of water versus temperature? We'll just talk about this. At every point on these lines, you're in equilibrium between the two phases. Equilibrium between the two phases, you can read the vapor pressure off the plot. The vapor pressure at this temperature is there. The vapor pressure at this temperature is there. That is the plot of vapor pressure versus temperature. So it's also the plot of K, the equilibrium constant, versus temperature. At every point along this line, it's in equilibrium. So at every point, there's a K. K varies with temperature, as we know. So, oh my goodness, I just thought of a great exam question. You know K, you read K off the plot, right? K is the partial pressure. You can read it off the plot. So if you know K, you know what? Another important parameter. Delta G standard only. The standard state free energy is related to K. Not delta G, not just any old delta G. The standard state. So you know the standard state free energy difference at every point on that line. That's the kind of question I like to ask, as you know. I want to bring everything together. So ask you about standard state. We'll do it. In fact, we'll do that in a second. Okay? So we understand that one. That is the, I got a spinning bracket for some reason. That is the pressure versus temperature. That's K versus T, or pressure versus T. So here it is. Let's look at the vapor pressure. Vapor pressure, very important. I talk about it all the time. Why do I talk about it all the time? It's a neat case where the vapor pressure is an equilibrium constant. That's handy. So I can ask you about equilibrium constants and partial pressure, all that at the same time. So you know I love to do that. So think about this carefully. So now I'm just looking at the part of the phase diagram above the triple point. So there's the vapor gas equilibrium. Expanded it. This is for water. You can tell it's for water because this slopes backwards a little bit. So there's the solid in that little point. Now there's the critical temperature. So here I'm going to do it. Here's the temperature pressure. Here's the pressure volume. We just did it in a chem quiz. At the critical temperature, that's where you just see, a fraction of a degree below the critical temperature. You just start to see that wiggle, that discontinuity start to form in an isotherm, pressure volume isotherm. So that, the critical temperature. What if I go to a point above the critical temperature? We just did that in a chem quiz. If you're above the critical temperature, this is an isotherm above the critical temperature, pressure volume space. So you can see going from there into volume space, if it was coming out of the board, would go on a line up into volume space. And if you just flatten that out, there it is. It's if you took this and rotated it out into the board and went through that point. I don't know why I keep harping on this, because I don't care if you know that. It's just interesting to me. I have to have some fun, right? So here at 100 degrees, we know we're below the critical temperature. 100 degrees is the normal boiling point. That means if I were to write the, look at the pressure volume diagram there, I would see that discontinuity very pronounced. Condensation happens at this temperature. And I could read right off the line the pressure. I can bring that line all the way across, because this is pressure volume and this is pressure temperature. There it is, 1 atmosphere. That's what it looks like. So that is the vapor pressure. It's a K. It's the vapor pressure. When I see that line flattening out, that's the vapor pressure. That means I'm on a point along that equilibrium line in the pressure temperature space, the phase diagram space. Here I'm coming way down. So this is room temperature, equilibrium. There's still an equilibrium with the gas, but the equilibrium gas pressure is very low. Okay, so here it is all together in one space. Here's another vapor pressure or another equilibrium constant. And we can go even lower. Here we are at 5 degrees, just above the freezing point, and the vapor pressure gets very low. And if I go much lower, I'm going to be in the solid phase, and all bets are off in this picture we've drawn here. Okay, beautiful. We've looked at this before. How does K vary with temperature? Same answer, right? There's K versus T. There's P versus T. The pressures are equilibrium constants. We did that chem quiz already. Every point on that line, you're in equilibrium between the liquid and the gas, which is true under standard conditions. We did this. Standard conditions means, what's the partial pressure of water? 1 atmosphere. Liquid is just there in the pure state. If it were a gas or a concentration, this would be 1 molar or 1 atmosphere as well. Remember, in standard state, everything, everything present, products, reactants, everything is at 1 molar or 1 atmosphere, or it's present in its pure liquid or solid state. So we looked at this, which is true under standard conditions. You can set up standard conditions. Standard conditions does not have a T involved with it. Standard conditions is 1 atmosphere or 1 molar. I don't care what temperature you're at. So I can set up standard conditions at room temperature if I want. So if I did this at room temperature, that would be too much pressure. 1 atmosphere is too much pressure. That would be a Q much larger than the K. And we talked about that already. So let's put it all on one plot. Let's really work our brains here for 10 or 15 minutes, and then you can shut off. That's the point where if we were at 100 degrees, we would have Q equal to K, because those conditions, we have a K and a Q. If we're at that point, we're at equilibrium, and Q is equal to K at equilibrium. So the standard state at 100 degrees C, Q is K at 100. Remember, K is a function of temperature, and they're both 1 at that point there. You know the standard state free energy difference. If you know K, that's everything you put to get the standard state free energy difference. You put everything at 1 molar or 1 atmosphere, and you measure the free energy difference between them. It's not equilibrium in general. 1 molar everything, 1 atmosphere everything, that doesn't sound like equilibrium. This is the rare case that it is. 1 atmosphere at 100 degrees is equilibrium, and 1 atmosphere happens to be the standard state. So in this case, it's equilibrium, and the free energy difference between the liquid and the gas at 100 C is 0. You have to replay this segment in the lecture probably 100 times till you get it all. Okay, we're at equilibrium at 100 C. That's also the free energy difference, the instantaneous, the reaction free energy difference is 0. Why? This one's always 0 at equilibrium. That is the equilibrium condition. The free energy difference between the products and the reactants is 0. That is equilibrium. The entropy of the universe does not change. Let's go to a different point. Let's leave that temperature and go to this temperature. This temperature is 25 degrees C. But you could still be in the standard state at 25 degrees C. You could still have 1 atmosphere of pressure, couldn't you? You would be setting up an artificial condition, but standard state is an artificial condition. So you could set that up, and you would say, well, Q is still 1 because it's 1 atmosphere of pressure. K changed because you're at 25 degrees C now. K is a function of temperature. At 25 degrees C, what is K? Well, it's the equilibrium concentration. The equilibrium pressure is 0.03. So here the standard state free energy is greater than 0. And of course it is, because if you put 1 atmosphere of pressure, that makes the free energy of the water gas too big. It needs to go back in reverse of the way we've written it, back in reverse towards the reactants from the standard state. The liquid is favored. It's not at equilibrium. And yeah, duh, we're not at equilibrium. That's not on any of these lines. That's right there. That's solidly in the liquid phase. Okay, and if you measured it, 1 atmosphere, you'd say, well, yeah, that's not at equilibrium. The free energy of the reaction is greater than 0. Okay? However, down here, now I've dropped the pressure. So the pressure is 3/100ths of an atmosphere. And now we're in equilibrium. Every point on this line, Q is equal to K. We're at equilibrium. So Q just dropped from 1 to 0.3. K was 0.3 the whole time. So now Q and K are equal if you're at 25 degrees C and 3/100ths of an atmosphere. And you're at equilibrium. So delta G standard did not change. The reaction free energy is now 0 because you're at equilibrium at 25 degrees C. Okay? So if you understand that, you kind of get this. That's everything. That's Q, K, delta G, equilibrium, phases. Everything is there. So replay this segment, look at the learning goals, and see if you get that. In fact, draw this on a piece of paper with just the phase diagram and see if you can recreate all that from scratch. You should be able to do it. And do it with someone sitting next to you and explain to them what you're doing. Could just be your dog. I'm just going to talk about the atmosphere just a little bit, because this idea of gases and liquids is the most important thing that happens in the atmosphere. If you look at the atmosphere, I'm going to plot several things at once here. If you go up in altitude, the pressure decreases. That's this blue line. And here's the troposphere near the Earth, stratosphere, and the mesosphere. You're going way up in altitude. The ozone layer is in there. If you look at the temperature plotted in red versus altitude, that temperature drops as you go up. Here are mountain elevations around 10,000 feet. The temperature drops in general as you go up in elevation. We know why that is. We're going to talk about that in a minute. And then due to some atmospheric conditions, it goes up a little bit. And then as you get really high in the atmosphere, way upper atmosphere towards space, you know, this has to go way down in temperature. That's what makes clouds. So I'll just quickly go through this. I don't need you to know all of this stuff. But at 25 degrees C, the equilibrium partial pressure of water is 0.03 atmospheres. Turns out that's about 20 grams of water per water vapor per kilogram of vapor, per kilogram of gas. That looks like that. And when you have the partial pressure of water equal to the equilibrium pressure, you call that 100% humidity. So if you have 100% humidity, that means any water is in equilibrium with the gas, and you usually see the gas as fog or cloud or rain or something. You see the equilibrium happening when you're at 100% humidity because you're at equilibrium. Okay, take that as the standard. Ratio of Q to K is 1. Equilibrium of 25 degrees C. We're not always there. We're usually less than 100% humidity. So we have a Q less than K. But here we are in a normal condition. Q is much less than K. So we don't have 100% humidity. In fact, the ratio of Q to K here is 0.3, so we're at 30% humidity. That's a common humidity. There's not 1 atmosphere, or there's not 3/100ths of an atmosphere of water vapor in the air. There's only 9/1000ths of an atmosphere of water vapor in the air. We don't really see it. It's in equilibrium. It's the state that's not an equilibrium condition at 25 degrees C, 30% humidity. The liquid is favored. As you go up, we get this thing called adiabatic cooling, and we know what that is. If I'm going to go up in altitude, the pressure decreases. You have the gas expanding against, if you take any sample of gas, say this sample, and let it expand against the gases around it, it does work on the gases around it. If it does work on the gases around it, adiabatically, its temperature goes down. And that is why the temperature goes down as you go up in altitude, because any volume of gas that travels up the mountains cools off as it expands. And it'd go the other way. If you went down, if gas came rushing down the mountains, it would heat up. So you could go up because you cooled to 5 degrees, the amount of water vapor didn't change. You took that volume of water, the partial pressure or the number of grams per kilogram of atmosphere didn't change. So now you have a situation where Q and K are the same again, drop temperature, K dropped. This Q stayed the same because all you did was change the temperature, pressure a little bit. So now you're at 100% humidity again, and you get a cloud forming. Hey, Karen, we can do the cloud formation. Did you bring, oh, she brought me some isopropanol. So I made this demo for Karen. Karen, I just broke the safety glasses, and they're really important for this. Can you bring me some out? I'm going to take this to high pressure, so I want to have safety glasses on. I'll do it right here so you can compose the shot up in the booth. Karen, I actually made this demo for Karen. Put these magnets in tennis balls. I actually made, I think it wasn't even Karen, it was Lonnie back then. I made them for Lonnie, but Karen got to inherit this. I'm going to leave this demo with Karen. I showed it to her, and I thought it was a nice surprise, and she just said, You got me a demo? I have demos. So I'm going to put a little compound in here so I get some potential of having a liquid. I need some liquid vapor. So I'll put a little liquid in there. Just completely wet the sides. Get some good safety glasses on. And I went into my workshop and I just put a tire valve in the top of this guy here. And this is just a bicycle pump, foot bicycle pump. So I'm going to go to the situation. I can't take this and go up in the atmosphere. I can't do it that way. But what I'm going to do is make the pressure really high and then release it. So that's like going up in the atmosphere. I'm just going to go to low pressure by starting at higher pressure. If I can. Okay. Okay. So I'm increasing the pressure in this thing here. This is just like pumping up a bike tire. And I'm going to go to, I'm not going to go to huge pressure. I'm going to go to about 15 or 20 psi. So lower than the pressure in your bike tires. Okay? Now I have high pressure, and I'm going to go to low pressure very rapidly by opening this. And what we expect is inside it's going to cool off rapidly, adiabatic expansion. So let's see that happen. Point this away from you and me. Ooh. Look at that. But look at that. I made a cloud in the, we'll have to work on that part. Maybe we should just put a sheet right here or something so don't kill anyone. I probably could have held it. I was surprised by how much it was. So I made a cloud. I am Thor, the god of thunder. I have made a cloud. I'm probably not Thor, not a Hemsworth. I probably am a Marvel character. Is there an app that tells you which character you are in the Marvel universe? There must be. Okay, somebody take my picture. See which character in the Marvel universe. Which character do you think I would be? Spider-Man or not? I'll give you not Thor. Oh, I would be Iron Man, right? Tony Stark. I already got the beard. So beard, yes, check. Eccentric genius. Check. Viciously handsome playboy. Well, okay, most of them I have. That's, I think, where I would fit into the genre. Okay. Now, I know that you guys struggle with this. And when you see me do it down here, it looks easy. But as I've told you before, I'm not any smarter than you guys are. You made it into Berkeley. Some of you will go on to do fantastic things. What you see down here isn't smart. It's just experience, just practice. All of you guys can do this, what I'm doing here with practice. And this is at the point of your life where you're doing that practice very much. But I was watching the news the other night, and this guy was trying to explain adiabatic processes, and just, I was so incensed by his explanation, I paused it and took a picture of the television. So look at what he's doing here. He's trying to explain why we have these things called Santa Ana winds in California. Air comes gushing down the mountains, and what happens when it comes gushing down the mountains? It gets compressed, and if it gets compressed adiabatically, what happens to it? It heats up. This guy said Let's check out what this guy said. Adiabatic process. This guy probably has a degree in meteorology. He says, air drops down from the mountains, it's compressed. This adds friction to the air molecules, which heats and dries out the air. What? Imagine if you were to add friction. What would happen? Well, the molecules, the collisions would become very inelastic, so they would lose energy every time they collided. If they lose energy every time they collided, what happens to the temperature? Pardon? Drops. Heats and dries the air. What is he thinking? So don't believe everything you see on TV. Should have paid a little more attention in Chem 1. This, I have no idea what he was talking about. You understand it already better than he does. And since this is the University of California, we have a disclaimer here. WTF stands for Wednesday, Thursday, Friday. So there it is. We have our understanding of phases and the forces that of interplay between them. So we'll talk a little bit about the next thing. We'll just introduce the next thing because it's kind of interesting. And we have 10 minutes left. Hate to cram things into the last 10 minutes, but we're going to now continue on our roadmap of chemistry. We now understand phases very well. We understand stoichiometry, the matter interactions, how things react, what ratios they react in, how relative mass allows you to predict these ratios. We've talked a lot about this energy difference now. But we've kind of been ignoring this thing in the middle. When we talk about energy differences, we always bring them right next to each other and talk about them. And don't worry about where we are in the reaction. This is the progress of the reaction. We only talk about reactants and products essentially at equilibrium. After you've made them, what is the ratios between them? And how does that affect the free energy difference between them? Okay? But now, let's talk a little bit about that hill in the middle. These are learning goals. Oops. Oh, these are old learning goals. Oh, what the devil? Those were all the wrong learning goals. Sorry. Remind me to fix that. I'm sorry. If you we'll fix that and we'll repost the slide so you guys have the right learning goals. That was just an older lecture. So let's talk about our favorite reaction: hydrogen and oxygen going to water. We've seen it explosively go. We have looked at the standard state free energy difference between them, and we know it's negative. This is favored from the standard state. 1 atmosphere, and pure liquid water. You could talk about making it form gaseous water. Then it would be 1 atmosphere, and 1 atmosphere. You could look at that standard state free energy difference. But you know that standard state free energy difference is negative. It goes towards, this is the stable state. This is the downhill state. It's the downhill state. It's exo something. Exothermic if you're talking about enthalpy. Exergonic if you're talking about free energy. It's downhill. The products are lower in free energy than the reactants from the standard state. Started the standard state, everything 1. How do you go? Well, you go to not very many reactants and lots of products. Free energy of the at 1 atmosphere, the free energy of the reactants is way too high. It goes towards products. This is all thermodynamics. That's what we've been talking about. But this part, going somewhere, is not thermodynamics. Those are not, they're not state functions involved along this pathway. there are path-dependent functions like work and heat. State functions, you could define them in little doses, but these are different processes, and we call them kinetic processes. They're the processes of the nitty-gritty, actually the individual particles bumping into each other, and statistically, whether they react or not. All that mess in between here and here, all that messy stuff is called kinetics. I avoid it like the plague. I like thermodynamics because it's clean. Just the products and reactants. None of this messy mechanistic stuff of how it actually happens. But that's called kinetics. And there is a real uphill barrier between products and reactants. And we know that because we can put hydrogen and oxygen in a balloon and it just sits there. So we know it's downhill in free energy to go to the water, but it doesn't. And this is what prevents it from doing that. There's an activation barrier. There's an activation energy. I have to go uphill first and then down. So I'm trapped in this little well because there's this one here. Over here, there's some lower energy state. I just can't get to it because I'm in a pseudo-stable state. Remember, stable just means everywhere else is uphill. So I'm kinetically stable here. Kinetically stable, I don't go to my thermodynamic destination. How do we get it over that? Well, we give it energy. You burn, you give it a flame. You give the particles more kinetic energy. Give them more energy, they bounce into each other differently and harder, and then they can get over this hill and release more energy and make products. So that's called the activation energy, the activation barrier. That makes it into, now that you guys know what it is, you'll start using it. There's an activation barrier to most things. Going to the gym. I'd like to go to the gym. That's my natural state. Lower free energy overall, but it takes a lot of energy to get out of bed and go to the gym, doesn't it? There's an activation barrier there. Let's look at them. Here is the kinetic part. We looked at this already. Reactants, this is products. Products building up over time. This is the course of the reaction. Time, if you're talking about time, it's not thermodynamics. Time is not a thermodynamic parameter. You're at equilibrium or you're at the standard state. You don't know what goes on in between them. My George Babcock, my physical chemistry professor at Michigan State, a delightful human being and a good guy, and I could credit him with where I am now. He got me fascinated with thermodynamics and sent me on this career to be a physical chemist. And he said to me one day, in a little bit of a British accent, Mr. Kubinec, he was also quite formal, time, Mr. Kubinec, is not a thermodynamic parameter. I was in his office and he was trying to get the point across. Don't think about time if it's thermodynamics. Time is what it takes to get to equilibrium. The products build up over time. All of this is kinetics. After that, thermodynamics applies at equilibrium. Factors that affect this rate. How do I get over that barrier? Obviously, the initial concentration, the temperature. Go higher temperature, it'll go faster. A catalyst will help you. What does the catalyst do? A catalyst reduces this activation barrier. Same thermodynamics. Catalyst does not change K or delta G or delta H. Catalyst changes just this activation energy thing, this kinetic parameter. You get to equilibrium faster. You lower the activation barrier. You can do the reaction at lower temperature. Let's watch that happen. think the demo button was back here. Let's do the catalyze. Lonnie will do it for us. If I push that button, here comes Lonnie. So we're in Lonnie's lab. He's got platinum, and he's blowing hydrogen gas over it. That's all he's doing. This is a stream of hydrogen gas. It's blowing onto just a piece of platinum, piece of metal. And the reaction is happening. Why? We can tell it's happening. That, Lonnie, you're too excited today. back. Did I go back? I want to see it one more time. We're in the demo lab with Lonnie, where he's going to... Happened too fast, Lonnie. He's holding a piece of platinum. Let's just pause it. He's holding a piece of platinum in front of a stream of hydrogen. You can see this is a hydrogen gas tank. He's mixing it. Is he mixing it with oxygen? I don't think so. I think that's just hydrogen. So it's the oxygen in the air that's coming. So hydrogen gas is blowing out here. There's oxygen gas in the air. That's just a piece of metal. That piece of metal, the hydrogen adheres to it, and oxygen adheres to it. And then they're close together for a long time. And the reaction can happen on the surface because the surface kind of constrains them from bouncing all around. And that lowers the activation barrier, and the reaction occurs, and you can tell it's occurring because the enthalpy, it's releasing all that energy. It heats up the platinum because all that enthalpy being released is absorbed by the metal. That's a gorgeous chemical catalysis example. And it's all the time we have today. So we'll end there. We'll see you tomorrow morning.